Hello, welcome to my video, and today is the Olympiad level number series lecture 2, and we are going to cover modular arithmetic basis from its definition to its basic property, and finally to Fermat's little theorem. And yeah, let's get started. And so first the question is, what is modular arithmetic? Our the intuition comes from someone will draw a clock. You will see it everywhere here. Like if we consider modular 7, we can consider here a clock, and all the numbers can be correspond to one number here on the clock. For example, 0 is 0 and 1 is 1, and 7 can also be correspond to 0 because when we write down 6, all the first 6 numbers, and 7 can only be placed here, and we can further write 8, 9, 10, and yeah, that's how we define modular arithmetic. We see here the remainder of this list of numbers are all 3. We can see here 3, 10, 17. This list of number divided by 7 is all 3, and for this list of number divided by 7 is all 4. So we can write down a more formal definition. When we write A is congruent to B modular n, we mean A and B have the same remainder when we divide by n, and we can express it by divisibility. A minus B is divisible by n because they have the same remainder, right? So A minus B must be the multiple of n. Yeah. So we have the definition of modular arithmetic, and many times when we need to prove some basic facts of modular arithmetic, we can directly refer to divisibility because we know more about divisibility, right? Yeah. So we can prove some basic facts. For example, we can prove that A plus n is congruent to A more than. This is the same as proving this one, right? And we know that this is true because n divides n, yeah. And we can also prove that some basic facts. For example, given a and n, is an integer, and the set of integer b, the set of integer b such that b is congruent to a mod n, which means b have the same remainder as a, right? And what is b? The set of b, we can, if we still want to use the divisibility property, we know that b minus a should be equals to nk, and b should be equals to nk 加 a, nk plus a, which means that b is an arithmetic progression, and the common difference is n. B is an arithmetic progression like this. And we can also write the other side, like is an arithmetic progression. Yeah. And this is some basic exercise of the definition. And now we can also consider some other thing we see when we divide any integer by n. We can get the remainder of n is one of those numbers from 0 up to n minus 1, right? When we divide an integer a, for example, by n, we get the remainder must be one of these integers, and there are in total n such possibilities. So for each remainder, we get a set. As we've mentioned, we get an infinite set similar to this one. For each remainder, for example, if the remainder is 1, we get an infinite set, which this infinite set fulfills this equation. And this infinite set, for example, a is 1 plus n, 1 plus 2n, and like this. And it forms an arithmetic progression, as we've mentioned. The common difference is n, and and it starts with 1. And it is the same as other integers, other remainder. And this is a way to divide the integer into classes, right? And rigorously we define the R's residue class. We define the R's residue class as the intuition is essentially the same. We define the R's residue class is the number, or is the integer set that remains R when we divide it by n. And we know that there are exactly n possibilities when we divide an integer by n. So there is exactly n classes, residue class, for when we mod n. Yeah. And we can also talk about some basic properties of modular arithmetic. For example, modular arithmetic is additive. This means that when we have this set of congruence, we can directly show that a plus b is congruent to r plus s mod n. And this is very easy to show because we can also use the property of the divisibility, right? This implies the divisibility, and as a result, we can write a minus r as nk, right? And a is nk plus r. And similarly, we can write b as n m plus s, right? As a result, when we add a and b, we have n times k plus m r plus s. And when we modular n, we got a minus b, a plus b is congruent to r plus s mod n, because this is divisible by n, yeah, which shows that modular arithmetic is additive. At the same time, we can show that modular arithmetic is multiplicative. What do we mean by multiplicative is that we see similarly when A is congruent to R mod n and B is congruent to S, we can get A times B is congruent to R times S mod n. This is what we mean by multiplicative. And it is also easy to show because using the similar technique, we can write a times b as n, as we shown here. We can write a times b as n times k plus r and n times n plus s, and this is with simple algebra manipulation we get this, and we know that this is divisible by n, so we conclude that a plus b is congruent to r plus s. A times b is congruent to r times s modulo n, yeah. So we've also proved that modular arithmetic is multiplicative. And we can also show something else. For example, we can show that modular arithmetic is, we can talk about some, similarly, we can talk about something about exponential, right? We can see whether modular arithmetic also forms some exponential rule, as we've seen in equality. And it turns out that indeed it also the rule, the exponential rule is true for modular arithmetic, because when we know n is a minus b is divisible by n, we know that a raised to the power of c and b to the power of c is a minus b times a to the power of c minus 1 plus a to the power of c minus 2, and until b to the power of c minus 1, right? This is a basic fact of algebraic factorization. It means that this divisibility holds for every a and b, right? And we know that n is divisible by a minus b, so n is divisible, n is a to the power of c minus b to the power of c is divisible by n, and this is the same as a to the power of c is congruent to b to the b to the power of c modulo n, yeah. And we show that, and in conclusion, we show that modular arithmetic is additive, multiplicative, and it also it can also do some exponential manipulation. So we see it is very similar to equality. The congruence is very similar to equality. And divisible, what we left is division, right? And it turns out that modular arithmetic can also do division, and we will cover this content next in the next lecture about inverse. Yeah.